So go ahead and type in the chat if you have any ideas for this question. Yeah, it does look like a generating function. No, it does not repeat every n because we have a times I. But it nearly repeats every n. So the most annoying part of this of this sum is that there's a GCD, because in a lot of sums we've seen before, we have like, especially number theoretic sums, we'll have like phi or tau, but then GCD is very annoying because it's periodic. And this is useful at times, but especially with a times I, this means that many normal techniques aren't going to work. So does anybody have any ideas for how to get rid of the GCD? Okay, so we can try looking at which terms have the same value for GCD. So we're going to try to split the sum based on the GCD of n and I. So if we do that, we might get something like this. Actually, so what I'm doing here is I'm taking out the GCD as D. And then for each term, I'm only looking at the terms which are divisible by D, because those are the ones which have the GCD of n and I to be D. So this expression is actually incorrect. So, but it has the right idea. Can somebody tell me why it's incorrect, first of all? So, no, it's not incorrect because of I equals 0. So the main problem here is that the coefficient of I over x to the I just isn't GCD of I. So if we consider the coefficient of I over x to the I on the next slide, it's actually going to be the sum of D divides GCD n of I, n and I of D. Does that make any sense? Because we're counting I over x to the I in every sum of D where D divides GCD of n and I. So for every extra term of I over x to the I, we're adding an extra D. So that's why the coefficient is going to be D divides GCD of n and I. But we actually want it to be GCD of n and I, not whatever that is. So we have to change the coefficient to something else other than D. So this may look a bit unmotivated, but if you did last week's homework, you should have seen that the sum of D divides n of phi of D is going to be equal to GCD of ni. Have you guys seen this before? So the sum of D divides n of phi of D is n. So this was one of the exercises in last week's homework. So I recommend trying to prove this in maybe after class. You can prove it by double counting. Or, yeah, double counting should work. So now, once we have this, we can write the original sum as f of n is equal to I equals 0 to infinity of I over x to the I times sum of D divides GCD ni of phi of D. So here I'm just replacing I'm replacing the GCD NI with this phi sum. So now I have a sum and a sum. The natural thing to do is sum swap. So the first few steps are just explaining motivation. Really, you can just skip directly to this step with the phi of d. So the point is you can express GCD of n and I as a sum of phi of d's. And since we have a sum and a sum, now we can sum swap to make the sum easier. So this sum swap is going to give sum of d divides n of phi of d times the sum from I equals 0 to infinity of di over x to the di. So the insight is actually pretty easy to deal with. We did this last class. I mean, we did this in summations A. So recall that the sum I equals 0 to infinity of I over x to the I is going to be x over x minus 1 squared. So the inside summation is actually going to be if we replace the x with x to the d and then multiply by d. So it's dx to the d over x to the d minus 1 all squared. So if we plug that into our expression for f, we're going to get f of n is going to be sum of d divides n of d phi d x to the d over x to the d minus 1 all squared. So f of n is composed of this term repeated for every single factor of d. I mean, for every single factor of n. So now, given this form, what should q of n, qnx be? So qnx is the denominator, remember. So in other words, we have a bunch of fractions right now, and we want to make qn of x the common denominator. So we're taking the LCM of all the denominators. So with this in mind, what should qn of x be? Okay, I guess something you can notice is that if d is equal to n, the denominator is going to be x to the n minus 1 all squared. But then if you plug in any d divides n, we know that x to the d minus 1 divides x to the n minus 1. So x to the d minus 1 squared divides x to the n minus 1 squared. So our common denominator should just be x to the n minus 1 all squared on the next slide. Does that make sense? This is just trying to find a common denominator. So since we found our common denominator, we can go ahead and multiply our expression by qn. And if we do that, we should get pn. That means pn of x is going to be, if we scroll down, pn of x is going to be sum of d divides n of d times phi of d times x to the d over x to the d minus 1 squared. And then we multiply by q of n, qn, which is x to the n minus 1 squared. So the d phi of d, x to the d are already in simplest form. But note that x to the n minus 1 squared over x to the d minus 1 squared is actually the square of a geometric series. So we get that the latter term is going to be 1 plus x to the d plus x to the 2d all the way to x to the n minus d all squared. So yeah, as Aaron pointed out in the chat, this is a very nasty expression. But luckily, we only need to find pn of 1. So when we plug in 1, the d phi of d remains constant, the x to the d completely disappears, and the last term is just going to be n over d all squared. So simplifying a bit, this is going to be n times the sum of d divides n of phi of d times n over d. So does anybody have any ideas for dealing with this sum, which looks a lot easier than the original sum? This is a topic we learned last class. Yep, it's convolution. And there's no need to message me privately. You can just say it in the chat. So this is convolution. So what that means is that we only need to consider prime powers as we did last time. So let's try plugging in p to the k into this expression. So if we plug in p to the k, we're going to get something of this form, namely sum of d divides p to the k of 5d times n over d. So when we plug in d equals 1, it's going to become p to the k. When we plug in d equals p, n over d becomes p to the k minus 1. 5d becomes p minus 1. And then now every time we increment d's exponent by 1, n over d is going to decrease by a factor of p, and 5d is going to increase by a factor of p. So actually, all the terms besides the first one are going to be p to the k minus 1 times p minus 1, which makes the entire expression as a whole p to the k minus 1 times p plus k times p minus 1 quantity. So this is pretty easy to verify. In case I'm going too fast, I'll give you guys a moment. So are there any questions so far? Okay, looks like no. So now remember that we want that 2019 divides Pn of 1. So this means that we need that 3 and 673 both divide Pn of 1. So if a prime q were to divide Pn of 1, we would either need q divides n or q divides p plus k times p minus 1 for some p divides n by our formula. And k here denotes the power of p inside the prime factorization of n. So we just need to find suitable terms in our prime factorization such that we'll recover both 3 and 673. So how can we get 3 in the prime factorization? Remember, this means that either 3 divides n or 3 divides p plus k times p minus 1 for some pk pair. So we could just have a factor of 3 inside n and be done with it. However, note that if our prime factorization of n includes 2 to the 1, then p plus k times p minus 1 is actually going to be 3. So this actually produces a valid tuple. Does that make sense? So that means we can just set n to be divisible by 2. And then Pn of 1 is going to be divisible by 3. So now let's deal with 673. So we either have 673 divides n or 673 divides a pk pair such that p plus divides p plus k times p minus 1 for some pk pair. So now these are just details, but basically if we have k to be greater than 1, then p to the k is going to be very, very big. So that will produce a very large n, which isn't good. So in other words, we should probably have k equals 1. And in this case, if k equals 1, p equals 337, which is indeed less than 673. So that means if n is divisible by 337 to the 1, then it's going to be, then Pn of 1 is going to be divisible by 673 by our formula. And hence, since it's multiplicative, our final answer is just 2 times 337, which is 674. So are there any questions? This was a pretty involved problem of the week. Okay, looks like there's no questions. We went a bit fast, so this will be in the transcript in case you want to review it later. And now we're going to move on to basic sequences with Daniel.
Can everyone hear me? Okay, good. Yep, we'll start off with some basic sequences. The most basic sequences with a lot of structure are arithmetic and geometric sequences. So just some refresher on the definitions. An arithmetic sequence is a sequence in which the difference between any two consecutive terms is a constant. And so we can write the terms of an arithmetic sequence as in terms of the first term and the common difference. I think you're going to need to refresh that. I just Yep. So we can write the terms of an arithmetic sequence as a plus b, a plus 2d, a plus 3d, and so on, where a is the first term and d is what we call the common difference. And a helpful tip that can help you calculate the terms of an arithmetic sequence is that each term is the average of the two adjacent terms. And similarly, we have geometric sequences. For a geometric sequence, the ratio between any two consecutive terms is a non-zero constant. And we can write it in terms of the first term and the common ratio now. The form is shown over there. And as with arithmetic sequences, we have a special property of geometric sequences where each term is the geometric mean of the two adjacent terms. And in general, it's very useful to write arithmetic and geometric sequences in terms of one term and the common difference ratio, because these two numbers describe the entire sequence. And so we can set up equations involving a very small number of variables that we should hopefully be able to easily solve. So let's move on to our first example, which is a problem from the 2003 AMY. I'll give you a little bit of time to read over this. Well, the numbers end up being fairly small, but I don't think it's reasonable to guess and check this. So to get started, we should try to assign some variables to the terms of the sequence. So as Aaron suggested, to set the second term b, we can do something slightly different. So the first three terms form an arithmetic sequence. The most obvious thing to do would be to set them to a plus d, and a plus 2d. But we can be a little cleaner with that by writing them as a minus d, a, and a plus d instead. The reason we do this is because the second three terms form a geometric sequence. And so if we use this choice of variables, the fourth term looks a little bit cleaner than it would if we set the first term to be a. And now the four terms of our sequence are as follows: a minus d, a plus d, and a plus d squared over a. Does everyone see where we got these expressions from? We essentially just took the information that the arithmetic and geometric structure of the sequence gave us and assigned variables accordingly. So we actually have an equation between the first and fourth terms. Their difference is 30. So now we have an equation relating a and d. The difference between the first term and the fourth term is 30. So now the first thing that we should do is clean up this equation. Can we move to the next slide? Yep, so we multiply both sides by a and simplify the equation. So now we get that d squared plus 3ad equals 30a. And now we want to be able to find d and a from this equation. Now, if you look carefully at this equation, If we try to solve for d in terms of a, we get a quadratic, and that can be fairly messy. But if we try to solve for a in terms of d, this is just a linear equation. So we should do that instead. Let's solve for a in terms of d. If we do that, then we get this expression. A has to be d squared over 30 minus 3d. Now, this is very helpful because we know that both a and d have to be positive integers, since all terms of the sequence are positive integers. Now, d has to be at least 1, since it's a positive integer, but now it can't be more than 9. Otherwise, a would be negative. That means that we know that d is some integer from 1 to 9. So now we only have 9 choices of d to check, and this is fairly reasonable. We can reduce the computation by a little bit. If we take a look at the expression for a, we know that the denominator is divisible by 3. It's 3 times 10 minus d. In order for a to be an integer, the numerator has to also be divisible by 3. That means d squared is a multiple of 3, which means that d is a multiple of 3. Yep, so now we can knock out everything that's not a multiple of 3. It doesn't take too long to notice that d has to be divisible by 3, and that cuts down on 6 of the 9 cases. So it's a reasonable use of time. So now we just know that d has to be 3, 6, or 9. So let's just test them all. Well, if d equals 3, that gives you a is 3/7, which is not an integer. So this isn't a solution. If d equals 6, then we can put it in and a equals 3. But the first term is a minus d. And since all the terms are positive, this doesn't work. And then we're only left with one case, which is d equals 9. And that gives us a equals 27, which is good. Yeah, I think a certain degree of guess and check is necessary in this problem because we only have one equation in between two variables. We have to use the fact that a and d are integers in order to pin down the values of a and d. If a and d were any real numbers, then we would have infinitely many possible choices. So since a equals 27 and d equals 9, and we know all 4 terms of the sequence in terms of a and d, then we can write out all 4 terms of the sequence. 18, 27, 36, 48. The numbers aren't that large, but I doubt it would be easy to guess and check this one. And finally, the answer would just be the sum of the 4 sequences, terms of the sequence, and that ends up being 129. Does anyone have any questions about this problem? If not, then we can move on to the next problem. A minus d being greater than 0. Oh, yes, that is true. My bad. Yeah, a minus d greater than 0 automatically kicks out 3 and 6. But you would have to actually calculate the values of a in order to know what, in order to check if a minus d was negative. So we can move on to this problem from the 2004 AME. A very similar problem was also on the 2016 AME. We have that in the problem set for this week. But if you haven't seen them, then you can read through them right now. So let's get started with what we know. All we know is the first term, the sum of two terms way back in the sequence, and then the structure of the sequence. So let's start with the first couple of terms of the sequence. We know that A1 is 1, and the first three terms form a geometric sequence. So yes, please don't spoil yet. It's not completely arithmetic or geometric, but we can write the sequence, first three terms. No spoilers, stop. Okay. So we can write the first three terms of the sequence as follows. And now, since we know that A2, A3, and A4 form an arithmetic sequence, we can write it as follows. We know that A4 has to be twice A3 minus A2. This is a general property of arithmetic sequences. You can rewrite this, if you need explanation, you can rewrite this as A4 minus A3 is equal to A3 minus A2, which is the definition of the arithmetic sequence. So we plug in the values and we can get the next term. Well, now A3, A4, and A5 are a geometric sequence. And given two terms of a geometric sequence, we can get the next term and, with the equation shown. We square A4 and divide that by A3. And we keep this factored, so it's nice and clean, and it's 2r minus 1 squared. And now we use the fact that the next three terms are an arithmetic progression. So we can calculate A6. And notice how we kept everything factored. This keeps all the expressions clean, and it's especially important when we're doing the geometric calculation, because we're going to have to divide something by something else, and it's not easy to see how this divides out if we don't have it factored. Next, we go and find A7, which we can compute since A5, A6, and A7 form a geometric sequence. So here you can see why keeping it factored is useful. If we had these expanded, then it would be very hard to tell what exactly the expression would be. But since it's factored, the numerator and denominator cancel nicely. And then we can continue as follows. After calculating this many terms, you can start to see a pattern emerge. So I'm going to omit the calculation, but can you scroll down a little bit? Yep. So it goes like this. And now we have an equation that A9 plus A10 is 646. So let's so we get an equation for R. Now this is a quadratic, and you can solve it, and you take the positive solution, R equals 5. Yep, alternatively, you can factor it and eyeball the solution, and then you can convince yourself that the quadratic, the other solution of the quadratic is negative, so we don't need to worry about it. So now, since we know that R equals 5, we can calculate every single term of the sequence. The other one, I think, is negative 25 over 36 or something. It's not going to give us a sequence of positive integers. So now that we know what R is, we can calculate every single term of the sequence using it in the same manner as we have done before. So I'll omit the calculations here, but we can since we know what all the numbers in the sequence, we just keep on plugging and chugging, and we can find that the largest term of the sequence less than 1,000 is a sub 16, which is 957. Does anyone have any questions about this? Yeah, so I omitted a lot of the computations above, but I'd recommend trying these calculations on your own, both getting to the equation a9 plus a10 is 646 and calculating the largest term less than 1,000. It's a good exercise in keeping expressions clean and factored, essentially calculating things efficiently. Well, we'll move on to our next topic, which is recursions then.
So I guess I'll just go a little bit about what recursions are, if you don't already know. So a recursion is just a sequence where each term is defined by the previous terms. And so in the problems that follow, there's going to be a lot of different types of techniques that we're going to use. There's not going to be just one technique that works for all, but a few things that we can try to use are periodicity. So checking if the sequence returns to its initial values at some later time. Large scale behavior, just like as a whole, what happens to the sequence. And so generating functions, we're going to do an example where we use generating functions. And so it would be helpful if you remember some of the techniques we taught about generating functions last week. So with that, I guess we'll go to our first question. So it's this problem from the 2012 Amy, so I'll give you a moment to read it over. Okay, so if you look at this, there's not anything immediate that you can see, like for how to evaluate F1001, right? So the idea is to just start calculating the first few terms, like see what happens in the sequence. So we already have F1, that's 2/3 minus 3 over 3x plus 1. And so then if we go and calculate F2, we're just applying the function a second time. So this is 2/3 over 2/3 minus 3 over 3 times 2/3 minus 3 over 3x plus 1, all plus 1. So if you simplify that, it's equal to 2/3 minus 3x plus 1 over 3x minus 2. So I'm not going to go about like simplifying that, but that's what happens when you simplify it. And so we still don't see anything useful yet. It looks a little bit similar to F1, but it's slightly different. So we're going to compute another term. So if we compute F3, and we evaluate that big fraction there, it's just equal to x. And so what that means is that if F3 is equal to x, then if we try to find F4, right, F4 is equal to f of F3 of x. So F4 is just f of x. So that means that the sequence is periodic every 3. So on the next slide, I wrote that the period is 3. And so then 1001. So what would F1001 be equal to then? Just someone say in the chat what they think F1001 would be equal to. Yeah, so it's F2 because 1001 is 2 mod 3. So it's equal to F2. And we calculated F2 above. So we have 2/3 minus 3x plus 1 over 3x minus 2. And in the question, it said that this is equal to x minus 3. So we set that equal to x minus 3. And now we just have a simple equation to solve for x. So we first would just clear the denominators by multiplying by 3 times 3x minus 2. And so the equation becomes this. And so after we simplify this, it becomes 9x squared minus 30x plus 25 equals 0. So what's the solution to that equation or solutions? Yeah, so it factors as 3x minus 5 squared. So the only solution is x equals 5/3. And so our final answer was 8. And I think someone was asking the chat how it was a number 11, and I think that's just because it's from 8 years ago, so the tests have gotten harder, I guess. So does anyone have any questions on this one? Okay, I guess not. So we'll move on to this next question, which is a much more challenging recursion question. So does anyone have any ideas for where to start? Or like, does this recursion, or I mean, not recursion, I guess the sum in the question remind you of anything? I guess if you remember back to last class, we covered a recursion that was a little bit, that was pretty simple. It was similar to this, yeah. So the Catalan recursion looks very similar, right? So that's Cn plus 1 is the sum of Ck times Cn minus k. And that looks pretty similar to both of these sums in the question. So so an idea would be to try to use a generating function like we did in the previous class. So we're just going to let a of x denote the generating function for a. And so if we go back to the sum in the question, I think Christopher was suggesting this to combine the terms in the sum. So we can just combine them into a single sum here, like this. And so does anyone have any ideas for what to do with this? Well, we can't just plug in Catalan because this sequence is not the Catalan sequence. It's just that the sums look pretty similar. Yeah, it's not. So our recursion is completely different. We don't know what the sequence is right now. We're trying to find out what its general term is by using a generating function. So the problem with this sum is that it's not just a product of two terms. It's a product times the sum ak minus 1 plus ak minus 2. So the idea is to define bk as a new sequence. So we define bk equals ak minus 1 plus ak minus 2 so that we get a very simple sum here. And after that, we can also define the generating function for the sequence b to be b of x. And so to get the terms in the sum on the previous page, like a n minus k times bk, does anyone have any ideas for what to do with these generating functions? Yeah, multiply. So if we multiply a of x times b of x, then we get the following. So if we multiply both of these generating functions, then it becomes a0 b0 plus a0 b1 plus a1 b0 times x plus a0 b2 plus a1 b1 plus a2 b0 times x squared plus dot dot dot. So, and from our recursion, a0 b0 is just 0 squared, and this coefficient of x we have here is just 1 squared from the sum that we were given in the question. And then we have plus 2 squared times x squared. So we can write this as a sum of n squared times x to the n. And now the question is to try to find what the sum of n squared times x to the n is as a generating function. So does anyone have any ideas for how to find that? Preferably using some of the generating functions we found in last class. So an infinite, so does anyone else have any ideas for how to get a quadratic term basically here? Yeah, n choose 1 and n choose 2. So if we remember from last class, we have that, so we first have 2 over 1 minus x cubed is the sum of 2 times n plus 2 choose 2 times x to the n, and we can just expand that as a polynomial. So n squared plus 3n plus 2. And then we can also do the same thing for n plus 1 choose 1. So we also remember from last class that 1 over 1 minus x squared is the sum of n plus 1 choose 1 times x to the n. And the last thing we remember is the simple geometric series. So just 1 over 1 minus x is x to the n. And so how are we going to combine these to get the term n squared? Yeah, so we can just combine them, and so 2 over 1 minus x cubed minus 3 over 1 minus x squared plus 1 over 1 minus x. And if we use our common denominator of 1 minus x cubed, it's just x plus x squared over 1 minus x cubed. And so remember that's equal to a of x times b of x. And now the final goal is to find what a of x is. So we have what a of x times b of x is. So we want to relate a of x to b of x. Does anyone know how to do that, given the definition of b that we created? So we defined bk to be ak minus 1 plus ak minus 2. Yeah, x plus x squared times a of x is b of x. And so if you don't see why, that's because we can just write that b of n, we can substitute a n minus 1 plus a n minus 2 in our generating function there. And we can separate that into two terms like this. And so each of the sums is just a of x. And so we get x plus x squared times a of x. And so then if we just substitute this into a of x times b of x is x plus x squared over 1 minus x cubed, then we get this. And after canceling x plus x squared, we have a of x is 1 over 1 minus x to the 3 halves. And so now the question is, how do we find the general term of this generating function? And so we have the following lemma. And it's probably not clear to you why this is true, but it's a little bit complicated, but you can try expanding this. You can try expanding this with the binomial theorem. Yeah, it's very similar to the Catalan generating function. And the reason that is because you can also take a derivative of the Catalan generating function and obtain this. So if you want to do it without calculus, you have to try expanding this with the binomial theorem. And so it's not that important. Like the main part is using the generating functions to find this this 1 over 1 minus x to the 3 halves. The rest is just answer extraction. So now that we have the expansion of this generating function, we can just write A2018 down. So A2018 is 4037 over 4 to the 2018 times 4036 choose 2018. And the question asked us to find the largest power of 2 in the denominator. So right now there's 4036 powers of 2 in the denominator, but there's also some powers of 2 in the numerator from the 4036 choose 2018. So we can calculate how many powers of 2 are in the 4036 choose 2018. Brian, can you scroll down? Yeah. So if we calculate how many powers of so we're just using that 4036 choose 2018 is 4036 factorial over 2018 factorial squared. So we basically just find the number of powers of 2 in 4036 and subtract 2 times the number of powers of 2 in 2018. And both of these, I'm sure everyone knows how to do here. So if we just calculate both of these, the first one comes out to be 4029, and the second one comes out to be 2011. So if we subtract, we get 4029 minus 2 times 2011, which is 7. So there's 7 powers of 2 in the numerator. And so if we just subtract those 7 from the 4036, the answer is 4029. So does anyone have any questions on this? Yeah, the question asked for the number of powers of 2 in the denominator. Okay, if there are no questions, we're gonna have a 5-minute break now.
So a linear recursion is a special type of recursion of the form a sub n is equal to c1 a sub n minus 1 plus c2 a n minus 2 all the way to ck a n minus k. And these types of recursions appear all over the place. So, for example, Fibonacci is a very famous example of a linear recursion. So probably one of the most important things when talking about linear recurrences is to try to find a closed form for them. So that's what we are going to be doing today. So does anybody have any ideas before we begin of how one would find a closed form for this? Looks like not, so we're going to get straight into it. So first of all, we're going to, oh, by the way, you might want to copy this form down because we're not going back to this slide. So I'll give you a moment. Okay, and Brian, you can scroll down. So the first thing we're going to do is consider the characteristic polynomial of a sub I. So we have s is equal to the sum of I equals 0 to infinity of a sub I times x to the I. So similar to what we did in the previous question, we want to find a way to solve for s by using the recurrence. So what is c1x times s plus c2x squared times s all the way to ckx to the k times s? So somebody in the chat said s is actually not exactly s. So if we look at the coefficient of x to the n, that should say n is greater than or equal to k. So if you look at the coefficient of x to the n for n is greater than or equal to k in this expression, it's going to be c1 times an minus 1 plus c2 times an minus 2 all the way to ck times an minus k. So how this expression comes about is that the term in xs, which has power x to the n, is going to be has coefficient an minus 1. You multiply that by c1 and so forth all the way to ck an minus k. And by our recursive formula, this is just an. So it looks like this expression is going to be s. But the problem is that this is only true for n is greater than or equal to k. When n is less than k, we aren't guaranteed that the expression has the right coefficients. So we actually have that this is going to be equal to s minus p of x. And p of x is going to be some polynomial with degree less than k, which corrects all the coefficients of x to the I for I less than k. Does that make sense? So basically, like if the coefficient of x squared in this expression, say, was off by 2, then p of x would have the term 2x squared in it to correct it into what it's supposed to be, namely a sub 2. So p of x is sort of a correction polynomial. But now we have an equation with p of x in s, so we can solve for s. In particular, s is going to be equal to p of x over 1 minus c1x minus c2x squared all the way to ckx to the k. So we want to somehow find a generating function for s given this form. However, we already know how to solve this if, say, the denominator is a linear function. So we want to try to break the denominator up into linear functions. So we're going to factor it. Suppose that the polynomial in the denominator has roots r1, r2, all the way to rk. So this means that the denominator is going to be of the form negative ck x minus r1, x minus r2, all the way to x minus rk. So now that we have this, the last term should say x minus rk. So now that we have this form, we're going to use partial fraction decomposition. What this means is that we're going to split up the fraction into a bunch of terms, each with one of these monomials as the denominator. Note that I took out the ck because the tops are constants anyways. So with this partial fraction decomposition, I'm going to have s is going to be of the form some constant over r1 minus x plus some constant over r2 minus x all the way to some constant over rk minus x. And since r1, r2, all the way to rk are also constants, I'm just going to make it a bit simpler by calling each constant some constant mi times ri. You'll see why I did this later. So actually, this is slightly incorrect, because if some of the ri's are equal to each other, we actually have a slightly different partial fraction decomposition. So for now, we're just going to assume that all the ri's are distinct, and we're going to get back to what happens when they're not distinct later. So anyways, moving on, now that we have this form, we're going to write each term as its own generating function. So remember that the fraction r1 over r1 minus x is equal to the sum of I equals 0, the sum from I equals 0 to infinity of x over r1 to the I. So if we do this for every single term, we will get the below. S is going to be equal to the sum from n equals 0 to infinity of x to the n times the sum from I equals 0 to k. That should say I equals 1 to k. Of 1 over ri to the n times mi. So basically, the ith term of the inner expression is going to correspond to the nth term of the ith generating function we made with our partial fraction decomposition. So does this make sense so far? Any questions? Okay, I guess we'll move on then. So now that we have this form, remember that S is just a generating function for a sub I. So we can actually just equate coefficients. So a sub n is going to be alpha 1 to the n times m1 plus alpha 2 to the n times m2 all the way to alpha k to the n times mk, where alpha I is going to be equal to 1 over ri. This is just notation for convenience. So note that alpha 1, alpha 2, all the way to alpha k are actually roots of the reciprocal polynomial of the denominator, namely x to the n minus c1, x to the n minus 1, all the way to minus ck. So this polynomial is very special. It's called the characteristic polynomial of the recursion. And I heard a lot of people above say this. So this is how to derive the characteristic polynomial. And then you may be wondering how to find m1 through mk. Well, given such a linear recurrence, there's going to be some initial conditions, such as what a1 is, what a2 is, all the way to ak, and using those you can solve for m1 through mk. So now that we have this form, we're going to go ahead and address root multiplicity. So remember that when a root had multiplicity 1, we had a term of the form m over r minus x inside our expression. So let's see what happens if it has multiplicity for simplicity. So it's going to appear in the partial fraction decomposition as some linear function over r minus x squared, because that's how partial fraction decompositions work. So with this form, once we plug it into the generating function, it's going to become some constant times alpha to the n. We already have that term, but we're also going to get some constant times n times alpha to the n, because we're going to have some term which is some constant over r minus x squared. And as we've done multiple times before, this makes a generating function where each term is also multiplied by its exponent. So in fact, this idea is going to generalize. So if we have a root with multiplicity d, then in the closed form, the term corresponding to this root is going to be of the form p of n times alpha to the n, where p of n is a polynomial in n of degree d minus 1. So let's have a short example. If, say, c of x has roots 2, 2, and 3, then the general form of the recursion is going to be of the form a plus bn all times 2 to the n plus c times 3 to the n, because 3 has multiplicity 1 and 2 has multiplicity 2. So now that we've derived the general form for all linear recursions, let's see how we can apply it to some context problems. And Brian will take over.
All right, so let's start with our first problem about linear recurrences. So I'll give you a bit to look at it and say ideas in the chat, I guess. So so first, how do you begin by going about like a linear recurrence problem, right? Like, so we just, so, yeah, so well, first, we're gonna go a bit slower than that, but first we see that we want to use the characteristic polynomial that we just learned about, right? So as was just said in the chat, we have this characteristic polynomial of x cubed minus 6x squared plus 12x minus 8, right? That's just copying over the coefficients, essentially, right? And so now the important thing about the characteristic polynomial is what are its roots, right? And then as was noted, it's a perfect cube, actually. So you can factor it as x minus 2 cubed. right? So that means that essentially you have a root of 2 with multiplicity 3, right? So what does this mean about the closed form? What would the closed form look like? Like, so in particular, we, as William said, we have this nice thing that happens. So where if the roots were all distinct, then we could sum it as a product of power, a sum of powers, right? But we have that the multiplicity is less than 1. Is greater than 1, I mean, right? So in particular, this tells us that we're going to have this 2 to the n, but we also have this polynomial p because its multiplicity is greater than 1. And the degree of this polynomial is going to be 1 less than the multiplicity of the root. So that means that the polynomial is going to be degree 2. Right, so now all that remains to be done is, what is this polynomial? Right, so, well, we notice that in the problem, they give us the first 3 values of xn. Right, and so, well, we can convert these values of xn into values of p of n. Right, so we can find that p of 0 is -1, p of 1 is 0, and p of 2 is 1/4. Right, and so, well, now we see that all we're left with is just we're given that it's a degree 2 polynomial that passes through these 3 points essentially. Not quite, I don't think. But we basically just want to find a quadratic that passes through these 3 points, right? I don't think that's the right quadratic. Like, for example, if you plugged in 0, that wouldn't work. But well, the best, like the most straightforward way of calculating this is just, let's suppose that it's an squared plus bn plus c, right? And now you just have 3 variables in 3 systems. And so I'm going to spare you the calculation. It's the ending quadratic should look like that. So yeah, does anyone have any questions on that? I guess if we don't have questions, we can move on to the next question. So if you recall, we actually saw this question before in a previous week, but this time we're going to be solving it in a different way, right? If you remember last time, we just used some algebraic manipulations that eventually got us to our desired expression, right? But this time we're going to be using linear recursions, right? So, well, if you look at these equations, what do they look like? Right? Like these, so I guess 2 things to note. One is that this is in the linear recursions section. And so look, in particular, look at the left-hand sides of those 4 equations and also what you're looking for, right? Yeah, exactly. So x and y, you're raising them to successive powers, right? So we can basically treat them as if they were roots of some some characteristic polynomial with roots x and y, right? So since we already used x and y in the question, I used lambda to represent the variable. But the variable in the characteristic polynomial is not particularly important. But yeah, so now we have this sequence t sub n, right? And we essentially know the first 4 terms of t sub n, and we want to find the 5th term, right? So what does this tell us, right? Because we have this characteristic polynomial, right? But what does the characteristic polynomial mean in terms of the linear recurrence? Right, so if you remember what the characteristic polynomial is, it's basically just like a representation of the coefficients of the linear recurrence, right? So in particular, these coefficients are x plus y and negative xy, right? So we'll just write these as u and v for simplicity, right? And we see that we can get this recursion in t sub n. Right, so now that we have this recursion in terms of t sub n, how do we proceed? Right, so in particular, we remember that we look at the 4 equations they gave us. Right, the 4 equations they gave us are basically just the first 4 terms of t sub n. Right, so, well, yeah, basically you just plug this recursion into the terms that you have. Right, so you can get those equations that are there. Basically just expressing each t sub n in terms of the previous 2, right? And so now, if you look at this, you have 2 equations and you have 2 unknowns, right? So this should just be a nice system that you can solve, right? So you could calculate it, but I have it right here. So the u and v that you end up getting should be negative 14 and 38. Right, you can check that it works if you want. But basically, now what does this tell us? Right, this basically uniquely determines the recurrence. Right, this recurrence t sub n, well, now you know u and v. So, well, all that remains is to calculate t sub 5, because that's what the question was asking for. Right, and t sub 5, well, we just apply this same recursion again. Right, so yeah, we can get that, except negative 14, it should be flipped because yeah, because basically u is multiplied by 42, but yeah, that's basically the question. So yeah. Do we have any questions on that? No? Okay. Well, I guess we'll move on to the next question then, which is about weird sequences in general.
Okay, so for our final topic, we're going to be talking about weird sequences. So whereas a lot of the sequences we discussed before had some nice properties about them, most sequences are strange and elude an easy characterization. So these types of sequences require ad hoc methods or unconventional ways in order to solve them. However, we do have some general tips which can help you solve these weird sequences. For example, you can always try to compute small terms. This is a very popular technique on the AMY to engineer induct. However, in this case, whatever we engineer induct, we're also going to prove. And that's important inside Olympiads as well. So also we need to look at how the sequence behaves as a whole. Sometimes the sequence looks really strange if you only pay attention to how it's defined term by term. However, you look at it at a whole, you can notice some global patterns. Also always be on the lookout for manipulations. Factorizations can often make a problem much easier, and sometimes a simple substitution like A of n is equal to 1 over B of n can really help simplify how the sequence looks. Also, if the initial conditions are given, oftentimes they're just going to be some random numbers in order to extract an answer. However, sometimes the initial conditions can be very special, and you can test this out by replacing the initial conditions with your own conditions. And if your own conditions produce something much uglier, that tells you that the initial conditions are significant. And finding the significance can often help you solve the question easily. And finally, always try to prove sub-results just to have a better intuition with the sequence. So not all sub-results you get are going to be used. However, if you find out more and more about the sequence, it can often just automatically lead to the solution without even thinking about the end result. So with that all being said, let's try to solve the question. So this question is from 2017 CMIMC. I'll give you a moment to read it, and you can type any ideas in the chat. So you could try a few small terms. However, if you do it, you're gonna get something which looks pretty weird. So what we're gonna do instead is try to get some intuition by setting our first number to a perfect square. So why I choose a perfect square is because we have a floor of square root an, and it's really easy to understand what this is equal to when a of n is a square. So suppose a of k is equal to n squared. So now what's a of k plus 1? Yep, it's n squared plus n. And what's a of k plus 2? Yep, it's n squared plus 2n. So a of k plus 2 is going to be n plus 1 squared minus 1. And then after the third iteration, we're going to get ak plus 3 is going to be equal to n plus 1 squared plus n plus 1. I mean, plus n minus 1. So as you can see, if we start with the perfect square, it's going to take 3 iterations of this function before we get to a number with one higher floor of square root an, or ak in this case. So how about we try this, except with some number of the form n squared plus I, where I is relatively small. So what happens when we start with ak equals n squared plus I? I could probably say that I is also greater than 0. So this time, things occur much in the same way, except after 2 terms, we get ak plus 2 is going to be equal to n plus 1 squared plus I minus 1. So what this means is that after 2 iterations, we're going to get to a number with increased floor of square root a, which is good. But at the same time, the amount we are over the square decreases by 1. So the square increases by 1, the overshoot of the square decreases by 1. So this will be very important. So let's summarize our findings. After a square, n squared, it's going to take 3 turns to increase the floor of square root a by 1. And then after these 3 turns, we're going to overshoot the next square by n minus 1. And after a non-square, we're going to increase floor of square root a after 2 turns. But when we do that, our overshoot of this square decreases by 1. Does that make sense? So what I mean when I refer to overshoot is basically the term which is added to the square. So if we start at a square n squared, consider when the next time we will reach a square is. So it's going to take 3 moves to get to n plus 1 squared plus n minus 1. This is on the next slide. And so it's going to take 3 moves to get to n plus 1 squared plus n minus 1, as we just showed. And then after this, we want to reduce the overshoot to 0, which means that we need to reduce it by 1 n minus 1 times. So that's 2 times n minus 1 turns. And then after each of these pairs of turns, our argument of the square is going to increase by 1 every time. So the next square is actually going to be 2n squared. So since we start at 1, our next square is going to be 4, then 16, then 64, and so on. And that should say 4 to the n plus 1. And the number 4, re-explain which part? Sorry. So if you mean okay, so for the first bullet point, we're gonna start at a square n squared, and then we want to consider when we'll reach the next square. So it's gonna take 3 moves to get to n plus 1 squared plus n minus 1. And now we want to get to another square, which means that we want to decrease the part we're adding to 0. So because then we'll have a square plus 0, which is a square. So in order to do that, we remember that every time we increase our term by 2, our overshoot is going to decrease by 1. So we want to decrease by 1 n minus 1 times, which means we need to iterate 2 times n minus 1 more terms. And then the next term is just going to be n plus 1 plus n minus 1 all squared, which is 2n squared, and then plus 0, which is just 2n squared. So since a1 is equal to 1, which is a square, our next square is going to be 2 squared, which is 4, then 4 squared, which is 16, 8 squared is 64. So all our squares are going to be perfect powers of 4. And note that from our above argument, 4 to the n plus 1 is going to occur 2 to the n plus 1 terms after 4 to the n. This is just by plugging in 2 to the n into our formula above, namely 2 times n minus 1 plus 3. So as a1 is going to be 4 to the 0, 4 to the n is going to occur at position 1 plus 2 plus 1 plus 4 plus 1, all the way to 2 to the n plus 1. And it's easy to calculate that this is 2 to the n plus 1 plus n minus 1. This is just a geometric series plus some 1s. So now the greatest power of 4 less than 2017 is 1024. And using this formula, we know that a of 2 to the 6 plus 4, which is a of 68, is going to be 1024. But we don't want 1024. We want a number close to 2017. And remember that 2017 is very close to 45 squared, which is 2025. So we want to try to get to 2025. So remember by previous logic, A71 is going to be 33 squared plus 31, because after 3 increases, our argument of the square is going to be 1 more, and then we add n minus 1 as our overshoot. And then once again, after each pair of terms, the argument of the square increases by 1, while the outside overshoot decreases by 1. And we want to get close to 45 squared, but we're at 33 squared right now. So we need to increase the argument of our square by 12. So that means we're going to add 12 times 2, or 24 terms. So 24 terms later, we're going to get to A95, which has the square term 33 plus 12 equals 45 squared. And the overshoot is 31 minus 12, or 19. So A95 is 2025 plus 19. So now clearly this is greater than 2017, but it's not necessarily the smallest. So consider A94. A94 is 2025 plus 19 minus 44, because A94 has floor square root of 44. However, this number is actually less than 2017. So that means our answer is exactly 95. Are there any questions? Looks like no. So we're going to go to our final question of the day, which is a question from Romania TSP. So you can go ahead and read it and type any ideas in the chat. So some people are suggesting to try a few terms. So this is a pretty good idea. However, it looks like that the recursive formula is pretty complicated. So plugging in is going to be a real pain. So what we want to do first is simplify our thing slightly in order to plug terms in more effectively. So can you guys tell me any simplification we can do from the beginning? So I think that one nice thing we can do is substitute b of n is equal to 1 over a of n. So now minus 1 is, some people were suggesting to subtract 1. That's a good idea, but it simplifies the numerator of the right-hand side slightly, but not really the denominator. It's still going to be complicated. So instead, we're going to substitute bn equals 1 over an. And this gives a polynomial recurrence, which is much nicer than our fraction. So now given this, we can go ahead and plug in some terms to see what happens. So we have b1 equals 2, and I'll just quickly plug in some more terms. b2 is going to be 3, b3 is 7, b4 is 43, and b5 is 1807. So this sequence may look very familiar to some of you. Does anybody have any idea what the pattern is? Yep, as Max said in the chat, it's the product of the previous terms plus 1. So we have 3 is 2 plus 1, 7 is 2 times 3 plus 1. 43 is 2 times 3 times 7 plus 1. And 1807 is 2 times 3 times 7 times 43 plus 1. So now that we have this pattern, it's going to be pretty easy to prove it. So we see that b of n plus 1 is equal to b of 1 times b of 2 times all the way to b of n plus 1. So in order to prove this, well, we have a recursive relationship. Yeah, as somebody said in the chat, it's a famous sequence and it appeared in USAMTS round 3, problem 3. I think it also appeared in a Don Zagier question. So on the next slide, we rearrange our equality as b of n plus 1 minus 1 over b of n minus 1 equals b of n. So we did this just by subtracting 1 on both sides and then dividing by b of n minus 1. So now we try multiplying everything and it actually telescopes. So if we compute the telescope, it's going to be b1 times b2 all the way to bn is going to be equal to b of n plus 1 minus 1 over b of 1 minus 1. But b of 1 is 2, so this is b of n plus 1 minus 1, and we're done with our sub result. So now that we have this useful result, I think it's time we substitute an back in. So if we substitute a of n plus 1 back in, we get that a of n plus 1 is going to be equal to 1 over 1 plus b1, b2 all the way to bn. So that's equal to a1, a2, dot, 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 an over 1 plus a1, a2, dot, 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 an. So let's try simplifying this to see if there's anything nice about it. So a1 times a2 all the way to an over 1 plus a1 times a2 all the way to an. We can take out an a1 times a2 all the way to an, and then subtract the error term, which is a1 times a2 all the way to an squared over 1 plus a1 times a2 all the way to an. But the right term is actually a1 times a2 all the way to an, and then multiplied by an plus 1. So an plus 1 is going to be equal to the product of the first n terms minus the product of the first n plus 1 terms of our sequence A. So does anybody notice anything interesting about this form? Yep, it telescopes. So if we add a1 plus a2 all the way to an, it becomes 1 minus the product of the first n terms, which is indeed less than 1. So we're done. So note that we actually didn't even really consider the final result. We just kept finding some, we tried engineer, found some sub-results, and then the question just solved itself. So oftentimes in ad hoc questions, the important thing is to find the intuition about the sequence, and then once you get enough results, the question should become clear. So are there any questions about this problem? Can you explain what you mean? Okay, so in the second to last step, what we're doing is we're first splitting up the fraction into the product of the first n terms minus the product of the first n terms squared over 1 plus the product of the first n terms. And you can just verify that this is correct by putting it under a common denominator. And the square will cancel out. But then the right term, we're multiplying the product of the first n terms by the left-hand side. And the left-hand side is an plus 1. So what we're doing is multiplying the product of the first n terms by an plus 1, which is going to be the product of the first n plus 1 terms. Does that make sense? Yeah, so the second equality just comes from the fact that the second term is going to be the product of the first n terms. And then once we take out those first n terms, what we're left with is a1 times a2 all the way to an over 1 plus a1 times a2 all the way to an. And now we substitute back in the recursive form, which is equal to an plus 1. So it's the product of the first n terms times an plus 1, which is the product of the first n plus 1 terms. Are there any other questions? Okay, looks like no. So that's the end of the class. Thanks to everyone for coming. We're gonna stay for a few minutes longer to answer any questions.